I think we'll look back on this as the time when things just started working.
Four months ago, we announced Chai-2, the first AI model to design antibodies with double-digit success rates in the lab. This represented a 100-fold improvement over the prior state-of-the-art. We showed that we could design simple binders known as VHHs and SCFVs, but we wondered whether we could build models that could design full-length monoclonal antibodies, the same kind produced by the human body and the most common type of approved antibody drug. Over the summer, we started to see that our latest models could indeed design this modality, creating full-length mAbs, zero shot, right out of the model.
But still, there's a big difference between a binder and a drug. To put something into a human, to manufacture a molecule at scale, to make it safe for patients, there's a whole host of so-called developability properties that need to be satisfied. We're now seeing that our designs meet or exceed the most important developability properties of approved drugs. We see that our antibodies are highly expressible with high yields and high purity. We see good thermostability, low polyreactivity, low self-aggregation. For almost every target we've tried, we find a molecule that achieves key therapeutic developability features, zero shot on the first batch of designs without any further cycles in the lab.
We next asked the question, can these models solve problems that have been traditionally considered difficult targets for existing lab-based antibody discovery methods? We looked at two challenging classes of targets. First, we tried a class called peptide MHC, which is important for cancer. Uniquely binding a cancer peptide MHC is challenging. The goal is to target a short peptide while avoiding many similar sequences. This requires a model that is sensitive to changes down to only a couple of atoms. Testing just a single plate of designs, we found a binder to an important cancer marker, finding that the antibody binds the cancer mutant while avoiding the normal, healthy variant.
Another family, GPCRs, can be thought of like a Swiss watch. GPCRs use delicate mechanisms to respond to molecules and signal downstream actions within the cell. However, they're notoriously difficult to drug since GPCRs are hard to isolate from their natural environment in the cell membrane. They have multiple states they can flip between, and forcing a signal change requires binding in a highly precise manner. We designed antibodies to multiple GPCR targets, testing no more than a few dozen molecules. We already found functional hits.
We learn something new about our models every week. Using cryo-EM, we solve the structure of 5 antibody-antigen complexes designed by our models. For every case we tested, the model's prediction of the atomic level 3D structure was highly accurate, with precision in many regions below the width of a single carbon atom. This means we can design molecules entirely on the computer with a high degree of trust in the atomic structure that's being predicted.
It's a special moment for the field. In just a few months, we've seen the models go from designing simple binders to antibodies to full-length antibodies possessing therapeutic properties. What's emerged is a glimpse of a new paradigm, one where designs are conceived on the computer and predictive models approach the precision of the wet lab.